Are we gonna go the full hour though? I do have a dinner
We
at
don't
nine.
have to. Don't worry
Okay.
about it. We can cut it short. I think we're live now. Let me just
Okay.
double check. I think that's good. Uh, okay. Anyway, well,
Are
hello
you gonna?
everyone.
Oh,
Sorry.
nothing. Go ahead.
Yeah. All right. Hello everyone, and welcome to today's episode of Corecast. I am your host Tim.
And I'm Mikey, and I'm Mikey, your host for today. Welcome, welcome to another episode of Quirkcast. If you haven't already, please join our Discord channel. And wait, are you going to be checking the Discord channel for questions?
I guess
Or
I will be checking YouTube. Yeah.
okay, yeah, do check out our YouTube channel and ask us questions during the episode, and we'll get to them. So, without further ado, here's a brand new episode of Quirkcast. Um, so Yeah, I mean, when I just look at this title, is temperature an illusion? I just want to ask you, like, what are you talking about here? Why would temperature be an illusion? I can feel, obviously, like it was really hot today in New Jersey. It feels hot, so everyone has some notion of what temperature is. So it's kind of intriguing that you tell me that it's an illusion. Like, what is this? What does it even mean to say that temperature is an illusion? Are you saying that I'm not really experiencing these effects, or?
Yeah, I mean, definitely we know temperature by its proxies, right? Like today is hot, and then maybe yesterday it was cooler, and then if you take ice cubes out of the fridge is cold. You take it out, it's hot, and then you see that when it's hot, it melts, right? But one thing that always intrigued me is like we see the side effects of temperature, but what really is temperature, right? Like,
Well, what I learned in high school is that air is made up of a bunch of gas molecules, and these gas molecules like vibrate while they're in the air. And basically, the more motion there is in these air molecules, I interpret this as a higher temperature. Like when something feels hot, it's because the motion of those air molecules, reach a point where they become violent, and they start to interact aggressively with my skin particles, and it feels hot. What's missing from that description?
yeah, I would say all that is sensible and it's reasonable, right? Like it's like, hey, you look at air molecules that is randomly jiggling, and the amount of random jiggling is related to its temperature. Let's say, right?
Yeah, that makes intuitive sense to me. Like, so yeah, I guess in my head, like temperature is very closely related to energy. Like these air molecules have a lot of
Right.
energy, and that can hurt me if it's too energetic and I come into contact with it.
Right. I guess the problem I always have is how do you know what is the energy of the jiggling versus the non-jiggling? Like for example, like certainly the molecules on my skin aren't jiggling in the same way like the as the air molecules, right? But of course, if I put some hot air into contact with my skin will heat up. So somehow, different molecules they jiggle differently, but yet they could have the same temperature. I think that's the first hint that it's a little weird, right? Temperature. Somehow there's this universal property that captures the amount of jiggling, but that amount of jiggling is kind of not a very good definition, wouldn't you say?
Wait, why isn't it a good definition?
Because it's not well defined. Yeah, like I would say the only thing that temperature does is it gives you a proxy to look at effects. Like if I have a cup that's hot and I touch a metal that's cold, I touch them together. At some point, they reach the same temperature. That's the laws of uh,
Yeah, is that the
thermodynamics, right? Right. But now the molecules in the metal and the molecules in my cup ceramics, they are very different, right? So like,
yeah?
how do I know they have the same temperature? I only know that it's because they touch each other, and there was energy transfer. I would say that makes it a little ambiguous now. Wouldn't you say?
Yeah. So I guess from my memory, I remember like certain formulas that actually like we're taught that you can actually compute the temperature from quantities like energy and pressure and stuff like that. But I remember that those equations were always like very restricted, like for an ideal gas. If we just assume that these are like a bunch of billiard balls in the air bouncing around, then the definition thermodynamically can be made somewhat precise, right? But yeah, I guess
Right,
like
right.
when those molecules are caught up in like solid substances like my skin, is there an analog to like those ideal gas equations that apply for solids?
I mean, certainly there is. You can link it to. I think loosely speaking, you can quantify the amount of random energy, kind of like, oh, how much random energy is there other than the other energy, if that makes sense. There always this divide that you look at a system. There's energy that's not random and energy that's caused by random motion, and the random motion portion becomes, you can quantify it by temperature. It's kind of like a proxy for temperature. I think that's a reasonable definition, but if you dig a little deeper, I think it gets a little murky. So here's sort of a thought experiment, right? Yeah. So imagine I have a system of gas molecules. I say, oh, the box of gas molecules has one temperature. Yeah. But if I divide the system in half, of course, on average, the temperature will be equal. But what if by chance, the bunch of molecules on the left half of the system might be jiggling a little bit more? It's just, it's all random. And then right, and then the molecules on the right jiggle a little less. Would I say that all of a sudden now the left side of the molecules have a slightly higher versus lower temperature, right? You can see that, initially I say the whole box has one temperature. Now if I divide the system in half, well, the left has one temperature, now the right has a different temperature. If I keep dividing again and again, all of a sudden the entire box has just many different temperatures now.
Yeah, but would they not all be like roughly peaked at the same value? Like, of course, well,
Right. I would say it's because when you're dealing with sort of random quantities, now the temperature is not exactly more. It's just kind of, some sort of an average, right? And I would say the temperature of a system kind of depends on how you divide up the system. Wouldn't you agree?
huh. I mean, okay, if the number of particles is really, really, really huge in my system, and if I divide it only a small number of times, then that makes perfect sense to me, right? And I get that there's going to be some variation in the temperatures in the different, what you call them, in the different compartments, if you're like compartmentalizing
Right.
space.
Yeah.
But, yeah, why is this really a problem?
Yeah.
I can see how it might be a problem once you subdivide to like just having one particle in your box.
Yeah. I mean,
I'm not with that, but
it's just a little odd because a lot of physical quantities, there's a sense of what we call locality, right? Like if you can pin down a particle at its location and how fast it's moving, like the property is at that location. But temperature has this feeling that you have to zoom out a bit to get a number because
yeah, but that's not the problem. I mean, my understanding is that thermodynamics is essentially the physics of a many-body system. So I guess the idea that temperature becomes ill-defined when I subdivide the box too much doesn't really bother me. Is it not just like a regime? Isn't thermodynamics only supposed to apply to like many-body regimes?
Right, indeed. So I think so. So the first crack is that it turns out that temperature is only defined when you have infinitely many particles.
Infinitely many.
At least in the defined in the classical sense, right? Like because if I zoom in on individual molecules, temperature doesn't really make sense anymore. So you gotta zoom out, right? And once you zoom out, presumably you approximate a little bit. It gets smoothed out, and then up to the fluctuation, temperature is defined. You can define it as the mean or whatever, right? So there's a little bit of I would say there's a little bit of pretending going on, isn't it? Like you have to pretend that the gas molecules is random, and then you don't know the details of the air molecules. so that you
Mhm.
subscribe a temperature to it, so that you can describe it like in a probabilistic way.
Yeah, isn't it kind of just like defining an average? Like it's true, like what's the average of like one thing? It's kind of trivial. I guess here it's like ill-defined rather than trivial, but yeah.
Yeah,
Why
but
are you concerned about this?
I would say that there's a little bit of subjectivity going in now. Like what
Yeah,
if
yeah.
what if there's a demon that knows every single air molecules?
Uh-huh.
Like the air molecules is exactly following this really beautiful pattern. I don't know what it is. Maybe it's drawing a Buddha shape. Who knows, right? This
Mm.
demon is routing all the molecules to dance in a particular way. And to our eyes, maybe we think of that as just random motion jiggling around. But to the
Uh-huh.
demon, let's say Maxwell's demon, he is orchestrating all this. It's like a drone
Uh-huh.
dance of all the air molecules.
Yeah.
Maybe the motion is not random anymore. It's not really just jiggling. Yeah. So maybe in that sense, it's not really. Maybe we shouldn't use that motion as the temperature. Maybe in some sense, you cannot like to the untrained eye. It seems like the movement is random, but maybe to a more precise, if you have more information, maybe not. It's not so random anymore. Maybe
Wait, if it's not random, why does that mean that I guess so I guess the fundamental assumption here is that it's only temperature if it comes from random motion. But why do I need to stick to that? So like because it sounds like what you're talking to me is like you just like let's say it's Einstein's deterministic universe,
yeah,
right?
yeah, yeah.
And it's like billiard balls, right? Like yeah, sure, you could consider the collision of billiard balls on a table as like some orchestrated thing, like it literally in pool, right? You're trying to orchestrate a group of collisions that eventually gets you towards a goal. But why does that take away my ability to refer to this as temperature?
Right, because what I'm trying to say is temperature depends on the fact that you need to pretend that the system is random.
Yeah, wait, I guess that's the part that I'm stuck on. Why
Yeah.
do I need like even if this demon is orchestrating some very complex like orchestration of collisions, I think I would still feel the effects of that as hot the way I normally do.
Right. Yeah, but okay, let me give an analogy, right? Like imagine you have a rocket just going from planets to planets. Yeah?
Mhm.
Okay. If a rocket crashes into a different planet, you wouldn't say that it's because of random motion of the rocket. It's because the rocket
Uh,
is just happened to crash on planet A and B. But if there's a galactic being, I don't know, like a really large system that thinks about rockets and planets as tiny little molecules going on, then
yeah.
that from that perspective, from that zoomed out perspective, you could say that while the rock is just going randomly, it just happens to collide into the
Sure.
planet. It's just a chance, right? So
Uh-huh.
I guess if you zoom out, you can think of it as a temperature. Oh, it's just some random happenings, and by chance, some planets will get hit by rockets. But if you zoom in, you see that that's very intentional. Sorry, like someone was running a test, like a rocket crashed into a
Mhm.
planet. So descriptions are very different, right? On the one hand, one is a probabilistic random description,
Yeah.
but the other has not. It just has nothing to do with temperature at all.
Mhm.
Nothing to do with probability.
Okay, but I have a measuring device called a
Yes.
thermometer,
Yeah.
which I can use to measure the temperature. And isn't it true that if I use my thermometer to measure the temperature, it doesn't matter if this is some predetermined orchestral set of
Right.
events,
Of
right?
course. Yeah. In this example, your thermometer needs to be like a galactic scale. So the
Yeah,
rocket will randomly hit the thermometer and heat up whatever liquid that is.
yeah.
Right. So in
So
some
why does that if my thermometer measures this as a temperature, why can I not think of it as a temperature? Just why can I not just use that as a definition of what temperature is?
right. I would say it's because it somewhat depends on your temperature measuring device, right? Like imagine your temperature device is a lot smaller, microscopic, or somehow
Mhm.
knows about the trajectory of these molecules, which doesn't happen in
Yeah.
real life. But imagine it can anticipate, oh, molecules hitting it from one angle but not the other. Then
Sure.
it's not going to experience, the random motion as much. I mean, I think we talked about in previous episode. There's this how information changes how you may view the system. How random you see the system.
Hmm.
So in that sense, you could argue that there is some level of subjectivity of temperature.
Wait, no, wait. But like, the way a thermometer works, right, is because like you put the thermometer in a liquid, and
Yes.
then these random collisions is essentially affecting the pressure
Yeah.
inside the
Yeah.
thermometer, right, which is causing the mercury to
Yeah.
rise.
Yeah.
And
Yeah.
so if I just use my high school thermodynamic equations and translate this energy to some form of pressure, like if the energy can create an increase in pressure, like typically we think that okay, a random energy that's very random will increase the pressure, right? Because it's just going in every single direction. Um, but if it's orchestrated and predetermined, it's still going to increase the pressure, right? So
Right. It is. Right. It is because the thermometer does not care about the substance you put it in. It's not in cahoots with the system. It has no preference on the system. It doesn't have any prediction or any like complexity to know like you know what it's able to receive all molecules hitting it in all directions. Yeah.
sure, it's an unbiased, ignorant observer, right?
Right. But the question is, what is unbiased?
Uh-huh.
So I mean I think this is something you appreciate after learning a little bit of statistics, right? Like there's sort of this belief that oh, if I have a six-sided die, if I roll it, my anticipation is that oh, all six will be equal. Why
Hmm.
not? Because I don't care which side is on.
Yeah.
But the similar thing is, why is that the default? Why, like maybe nature likes one better than two? Why isn't there a preference?
Um, hmm. Yeah, I mean, like I remember, like it's said many times that, like, right, in a sense, thermodynamics is like a parameterization of our ignorance, right?
Right.
Um,
Yes. Yes.
so
I mean, don't get me wrong. I think it works superbly well, right? In our
uh-huh,
universe, somehow, if you have a six-sided die and you say, "Well, I don't know what it does," gee, I don't know what it does. It's actually a pretty good approximation to say, "Well, all six are equal," given that.
uh-huh,
And it's the same thing. Like, oh, if I see some air molecules, it's safe to say that it can go up, down, left, right, front, back, sort of
uh,
equally likely, without further
yeah.
information. But the question is, well, why?
Okay, you convinced me, I think, part of the way. I'm willing to admit that my definition of temperature requires me to assume that I know nothing about the motions, right? Um,
Right, yeah.
where does that like where does that take me astray, I guess? Like, what's wrong with just assuming that? Like, let me just okay, so let's say that
Mm-hmm.
someone like let's even say that like it doesn't even look random. Let's say that like some demon set up all these air molecules to go in just one direction, right? But I'm going to approach the problem as though I don't know that. And I'm still going to use my thermometer to
Right.
measure the temperature, and maybe it'll look a little different. But then, okay, that's my definition of temperature, so I'll just accept that. What's wrong with that?
Well, no, I don't think there's anything wrong with that. But I'm just saying that it's interesting now that temperature has to predispose on the fact that we are ignorant beings. We don't care
Yes,
about the details of the system.
sure, sure.
I think it raises an interesting hypothetical question. Is it possible, theoretically, that maybe some other beings that have much more knowledge about a system, let's say my cup, it looks like oh it's at 25 degrees Celsius. Maybe that being will perceive something totally different, and that notion
Hmm.
of temperature will be just completely something else. Is that
Okay,
possible?
okay. Hmm.
I would
Yeah,
say I
I can
hate
see
well
why that
yeah.
would be a philosophical problem for a super advanced being, but hmm.
well, I okay. Well, because this episode is is about quantum physics. I think we have
Yeah.
to bring that in, right?
Uh-huh.
And so the most extreme places with temperature, I would say, and the closest of temperature being a fundamental thing, I think it's a black hole. I think people working on quantum chaos and
Yeah.
quantum thermodynamics, for sure, we realize that black hole is a very interesting object. And it seems that, yeah, Mike, maybe you can just give the audience, I don't know, like a spiel on black holes and temperature.
Okay, well, I don't know too much about, but my understanding is that black holes have a well-defined temperature. Isn't this why Stephen Hawking is famous? Because he realized that, okay, stars have a temperature and stars turn into black holes. So how can it just be that, like, well, yeah, because, okay, so I guess to give some background, like, in classical general relativity, black holes are strange in the sense that they are one-way thing. They suction things in and they don't release anything, which means that classically, at least in classical theory, if black holes really behave just the way Einstein's theory predicts, then you would never be able to measure the temperature of a black hole because there would be nothing coming out of it. So it would just be like this empty space. And I believe Stephen Hawking realized, I mean, I imagine this was his thought process. It's like, okay, the star has a temperature. When it explodes, it has a temperature. But when it turns a black hole, suddenly it doesn't have a temperature? That doesn't make sense. How can temperature just disappear? And so he thought very carefully about this and came up with the area law that says that the temperature is proportional to the area. So that's my understanding, that the area that the temperature of a black hole can be made at least somewhat fairly well defined.
Right. But usually that's only defined for what people call like an external observer, someone who's really far away from black hole, who's very ignorant. Let's say in this example, compared to the gas molecule, who's very ignorant about the whole situation. He's just looking around the universe, like, here's some object here. Here's a black hole. I don't know if it's a black hole or not, but I can kind of see the temperature coming off from this object, right? But imagine this person now decided to take a plunge toward the black hole. Yeah. As he slowly fall in, he'll actually observe something else. So Hawking, for example, the Hawking radiation it only makes sense when you sit out very far and you see the black hole radiating out. But the belief is that as you fall into the black hole, you should see nothing unusual about that black hole, right? So at some point, as you fall with the gravity of the black hole, you free falling in, you will stop seeing this this radiation. And if as you pass through the event horizon, it's we don't know exactly what happens, but the general belief is that nothing actually happens. You actually you don't feel the temperature. You don't feel that.
Wait, sorry. Why wouldn't I feel the radiation? I thought even if I fall inwards, I'll still see
because
radiation.
Because you're free falling. You're not experiencing acceleration, right?
But I'm still going to experience like the Hawking pair created particles that are released from the horizon, won't I?
No, I don't think so. I think only in an accelerated frame. Like, in order for you to stay away from the black hole, you need to be accelerated in some sense. So I think if you fall in, you won't see the Hawking radiation. Hawking radiation is only at infinity.
Oh, is that, sorry, not to get technical, but is that related to the fact that it can be interpreted as an UNRWA radiation?
Yeah, exactly. So yeah. So just to clarify to the audience.
I didn't know that.
Yeah, just to clarify for the audience. In general relativity, Einstein's theory, combined with quantum physics, you generally see a temperature depending on how much you're accelerating, how much you're like, you feel like, I don't know, going down the roller coaster. You have that feeling, right? You will see particles getting pair created, and the math is basically exactly the same as Hawking radiation, right? And it tells you that and this is equivalent. Let's say the Hawking radiation is the same thing about temperature. It turns out that if you somehow interpret the situation differently, somehow you see a different temperature.
Okay, temperature's in the eye of the beholder.
A little bit.
It's a little weird, but in physics, there's a lot of things like relativity. Famously, is a statement that these observations depend on your point of view. So. why should I be worried that temperature is reference frame dependent?
Right. No, I think it goes a little beyond that. You can say, oh, it's reference frame dependent. Okay, relativity, blah, blah, blah. Okay. But this is actually a lot more than just space and time is a relative, because this goes to the idea of complementarity now. So this is a little speculative, but people generally.
Well, no, sorry, not to interrupt you, but I was going to say, like, if you believe, Harlow and Hayden's resolution to the information paradox, then the radiation is never random, right? If I have a powerful enough quantum computer, I can descramble it, and everything becomes predictable.
Yeah, and this is related, right? Because now we have two perspectives. One perspective is someone from the outside of the black hole. We say, well, I don't care about the black hole. It's just some object. And I never see the inside of the black hole because nothing ever comes out of it. I'm ignorant of the black hole's features. So that's why I see a temperature, because to me, the black hole is all scrambled up, like a gas in a box. But if I decide to take a plunge into the black hole, maybe I start to see old friends who went in. I don't know. Maybe they went in recently, right? Maybe I'll see old objects, like maybe an entire building, a planet, galaxies fell into the black hole.
You mean after you enter the event horizon?
Yes. Yeah. Okay. After I enter the event horizon, there's a chance that I could interact with that stuff. So what seems to be random on the outside, which is just radiation, heat. Now, once I decide to take the plunge, it's almost like I take that perspective of unscrambling the stuff on the black hole. Yeah. And all of a sudden, I don't see temperature anymore. I see, like, objects. So I feel like this is... I don't know if you agree. This is sort of a hint that...
What? Yeah.
Sort of a hint that the temperature is a bit of an illusion, isn't it? I don't know. Would you agree?
It's definitely... frame dependent. I agree with that. Yeah. The classical Harlow and Hayden's answer to your conundrum would be that yes, in fact, I don't even have to fall into the black hole to see what's coming out. If I just know everything that fell into the black hole and all of its trajectories, then I can actually, and I have a powerful enough quantum computer, I can actually, like, just like the way, like, when you delete something in your memory in a computer, like, right, that's translated to, like, the radiation particles that come off of the computer. If I had a powerful enough computer, I could reverse engineer all of that radiation and get back the lost data, right? But they argue that doing so would take longer than the age of the universe to complete. Therefore, it is genuinely random.
Right. Yeah. So. But yeah, I don't know how to think about that. So if in principle you look at something that looks like it's had some temperatures random, but then you can unrandomify it, whatever that means. Is it random or is it not random?
It's not random. No, it's not random. Yeah, but because I guess that's why Harlow Hayden thinks they say it's not random, but you can't distinguish it from random because it would take longer than the age of the universe to figure out that it's not random. Therefore, it is random.
So now it's like, it's a little weird, right? Now randomness sort of has a limit, but is this notion of something being random truly an objective, I don't know, definition? I don't know.
I think the part that's I'm having trouble with is, like, yeah, I understand that there's, like, this very nuanced kind of like difficulty in distinguishing whether something's random or not random. And I understand that the definition of temperature is based on the assumption of randomness. But what I don't understand is where this breaks. Where's the crisis here? It seems to me like
well, I'll bring a different perspective, right? Because in quantum physics, one will argue that nothing truly is random. There's no such thing as random, because random has this feeling that there's what we call information loss. It's like imagine I flip a coin. I get heads. Well, but if I go back in time, I say, well, it could have been tails. And if I flip heads, it would seem like the possibility of tails was lost. But quantum physics tells us that that's why there's a law of quantum physics that many people consider so sacred that it's more sacred than other physics law, is the preservation of quantum information. It says that if there was a possibility of heads and tails, even though you got heads or tails, that possibility is still in the system. Maybe it's somewhere out in the universe you cannot retrieve easily, but the fact that the coin could have been heads or tails is forever in the cosmos. It's completely unremoved, right? It can only, that information only spreads out, but it's never deleted, it's never copied, but it just stays. This is the principle of preservation of quantum information. So in that sense, that kind of tells you that randomness is at best an approximation, but even worse, classical.
Wait, hold on. I think we should clarify this though, because I think most people watching this would, if they're familiar with science communication explanations of quantum mechanics, they would associate quantum mechanics with randomness. And classical mechanics with non-random, and you're kind of saying the opposite here. Can you elaborate on that?
Yeah, I think it's a little difficult to grab. I would say quantum physics deals with possibility. I think randomness is a loaded term, because if you study the math, quantum physics is associated with this concept of wave function, which roughly speaking looks at all the possible outcomes. Like the particle might be to the left, to the right. The wave function encompasses both. It could be left or right at the same time, or maybe in the middle, or maybe a continuum from left to right. How much to the left, how much to the right? And then quantum physics says that just because you've observed a particle, let's say on the right side, does not mean that it's not on the left side anymore. This is the famous double slit experiment, right? Just because you see it on the right does not mean that it's not on the left. That possibility remains, and it's still almost like an invisible hand tugging and pulling the physics of the system. And generally, when people think about classical randomness, it's like a gambler. They're like, I gamble all my money on black, and they win or lose. Oh, that's it. The next gamble has nothing to do with the previous one, right? But in real life, actually doesn't work like that. In some sense, there's a little bit of a solace in quantum physics.
Hey, Tim. I think implicitly here you're assuming the many worlds interpretation of quantum mechanics, right? Because there are people out there who would say, yes, the wave function does collapse, and therefore the particle really only goes through one slit when I observe it. We know those people are wrong, but
well, I fully agree with you. Just those people are just wrong. I don't know how better to put it. There is no wave function collapse.
I think this is the thing that a lot of people miss when talking about quantum mechanics, especially in a to a popular audience, is that people like to say quantum mechanics is non-deterministic and random, and classical physics is everything is deterministic and you can calculate the billiard balls. But I think the point that's often missed in these discussions is that the wave function that you talked about in quantum mechanics, that thing is deterministic. The wave function is completely deterministic. It's just that the wave function contains all the possibilities. And we believe, people who really understand physics, I think, mostly believe that wave function collapse isn't really a thing. It's not like the wave function suddenly changes because you. So what we're saying here is that the universe, if you take the many worlds scenario, the many worlds interpretation, the universe is deterministic, but what we experience from it is kind of like a random sampling of one thing.
Right. Basically, we can't tell which part of the possibility we're sampling. I mean, in the multi-world interpretation, there could very well be a bazillion Tim Lu, feeling the different feelings, but there's no overlap. I can't communicate.
They're all valid.
Yeah, so I don't know the Tim Lu millionaire who flipped a coin 20 times and got it right, and I don't know, win $1 bazillion because of that. Or I don't know the Tim Lu that's homeless because, that person lost a lot of bets because he flipped the wrong side of the coin. Maybe they're all feeling something, but I don't know how they are feeling. So that's how the indeterminism in quantum physics is different from the normal one. They're not erased; they're there.
So are you really saying that the many worlds interpretation of quantum mechanics has a tension with our notion of temperature because of this deterministic character of it?
Yes, indeed. And this is the sort of the crux of the black hole paradox that was resolved, right? Like people believe that black holes have a temperature. And because if black holes truly has a temperature in the normal sense, it means that there's information loss, because every time it emit a light particle in let's say in direction 1, the possibility of direction 2 is gone. It didn't emit a radiation in the other direction. So then almost the black hole is erasing possibilities from the quantum system. But we know that it's not. Hawking was wrong. Susskind and other people were right that that possibility is not lost. It still exists in the world, but just lost in the substrates of the universe, the sea of possibility that takes the age of the universe to uncover. Like you were mentioning, it's too hard, but it's still there, I think.
I see. Okay. So I get that there's a philosophical crisis here. Yeah, somewhat with classical ideas of temperature. But it doesn't affect me though.
Well, it doesn't affect you, but I would say that this is where some of the modern research in quantum physics are, right? Like, so for example,
on that point, like what are people like? I guess the question is like, how is this not just like a philosophical curiosity? Like why is this actually having an impact on the way people think about things? Like, why isn't it just like why do people care about this?
well, I think I don't know. As physicists, personally, I find it interesting, but there are probably some other utilities too. But let me frame it this way, right? So in classical physics, when we say things are random, things are lossy, there's just this random noise in the universe. It's unsatisfying, right? Because it's like a gambler. You gamble on black or white, black or red, and you lost your money. You win your money. All that stuff is gone. The universe doesn't keep track of it. It's a little uncomforting. But now with quantum physics, you can actually have a theory on where that effective noise is coming from, basically. Because in classical physics, it's just like, it's just noisy. We can't predict stuff. So what? People kind of just shrug and ignore that deep fact that's unsettling.
Yeah, fact. That was pretty much my attitude towards it up until now.
Right. But I think the modern view is like, hey, look, you actually don't need to make any assumptions about the universe. If you just have a universe with quantum physics itself would generate what looks like noise, but isn't. Sure. That's the interesting bit, and that's not obvious to people. So the thought experiment is, imagine I have a quantum system. Okay. Let's look at classical first. Classical, in order to define a temperature, I have to look at a bunch of molecules, how they move, and do some statistical modeling, let's say, right? And that's my temperature. Yeah. But now in quantum physics, what I need to do is have a bunch of molecules interacting, right? And because quantum information cannot be lost, you can show that the information of each particle gets shared amongst each other, right? Yeah. And then what people do is you can single out the viewpoint of one molecule. Let's say I remove one molecule and look at what this molecule sees. Because the information of that molecule and the other molecule just keep getting exchanged by these quantum interactions. What happens is you will see an effective scrambling, almost like the black hole situation. It's like, because information is going left and right, it's hard for me to unwind them. So effectively, I see random noise. So effectively, this particle sees a temperature, and vice versa. Yeah. And because of that, you can there's a belief that you can actually subscribe a temperature to a single particle, for example. You actually don't need to average out multiple particles anymore.
Uh-huh. Okay, if I'm understanding this correctly, just to recap, like if I have like a bunch of particles and they're all entangled with each other quantum mechanically, then I can, deterministically compute the evolution of the system. But if I take away one of these particles, now it's like there's entanglement, but there's something missing. So now, if I ignore that one particle, then just the rest of the particles, there's like an irreducible ignorance to it, and so that affects the temperature. And so I can kind of define the temperature of one particle by what its effect on the system is on my ignorance if I take that particle away.
Yeah, precisely. And this has physical consequences, right? Because normally you would think that I can't define temperature for a single particle. It's just moving around. I can't, there's no average of anything. But now you can define a sort of effective temperature on how much ignorance I have about this particle, because quantum physics says that because information tends to get leaked out, but never destroyed. Information from this particle can exit, and it can gain information about different particles, in and out, in and out, in and out. And you can show that just because of that, there is uncertainty of what this particle is doing based on that, based on the quantum mechanical properties of the system. And that kind of answers this question. This question is, where did noise come from? And this existential question. At least I think that's useful.
Sure. Yeah. Okay. So quantum mechanically, because of entanglement, I can find a way to quantify the temperature of a single particle. Yeah. Okay. So I guess we're coming close to time now, but like, instead of the usual tradition of like asking what like lessons we've learned, I think maybe a little bit. I'm curious about, like, because I'm not that familiar with this research, but like there are people thinking about this. What would be like? Let's say the people researching, like, quantum definitions of temperature, and how to define it based on subdividing and entanglement and things like that. Like, what is the most exciting possible scenario for this? Like, right? Like, so, like, if we imagine that this research program is like, as successful as possible going into the future, like, what kind of is there, like, or is it just like a philosophical curiosity, or is there something that, like, okay, if we really figure this out, this is going to like advance our understanding of this and that, and like
my feeling is that because in our last episode we talk about how you can beat the noise by building these if you have more information about the system, you can potentially exploit it. You can extract more energy than you might anticipate. So the belief is, if you can understand the noise better, maybe the noise is not noise anymore, then you might be able to extract something more from the system than you would have thought. And this could be the key to making, I don't know, quantum computers to work.
Perpetual motion machines.
Well, I don't think perpetual motion machine, but like maybe like this could be the proper way to run computation, or to extract energy to build engines, or to really truly exploit materials of our world, which are quantum mechanical, because everything is quantum mechanical. So, but I think most theorists who are working on this probably just have the philosophical curiosity, myself included, probably. But I'm not a researcher at this point. But
fair enough. Okay, cool. I buy this. Yeah. Okay. So I guess. Yeah.
Yeah. Well, I guess we're coming to the end here. Well, on that note, I want to thank you everyone for joining us, and we'll try to have this next week as well.
Yeah.
All right.
Bye-bye.
Bye-bye.